Welcome to Unacademy, the largest online e-learning platform, and welcome to Unacademy Semester Exams. Unacademy, let's crack it. So, crack GATE and ESE with India's largest e-learning platform, Unacademy, and get subscription. Get the plus subscription and access unlimited live and recorded courses from the India's best educators. And the topic for today is from the Network Analysis and Transmission Lines Crash Course, Revision Part 2. Srishti Imitation Jewelers, good evening. Hi, welcome to Unacademy. Now, let me tell you about myself. I am sravan Kumar, having 7+ years of teaching experience and mentored more than 5K students for GATE and engineering services and also cracked GATE. Let me tell you the Unacademy Learning App installation procedure. Type Unacademy Learning App in Google Play Store and click on install. That's it. App get installed, and what do you get out of it? You'll get daily live classes, structured courses, live quizzes, unlimited access. And in iconic subscription, you have personal coach, study tracker, mains, question and answer practice, all benefits of Plus. And in Plus subscription, you have daily live classes, structured courses, live test, unlimited access as well. You can learn from the top educators of the Unacademy, as you can see. And in GATE and ESE, you have batches and year-long courses for ECE, aptitude, chemical, mechanical, CSIT, instrumentation, mathematics, electrical, civil, production and industrial engineering. In Plus subscription, you have all the benefits that you can see here, and in Iconic, you have all the benefits of the Plus with some additional benefits also. So you can opt for Plus for 1 month, 3 months, 6 months, 12 months, 16, 24 months, and you can use my code YSK10 to get the discount on your subscription, and I suggest you to opt for 24-month subscription. In Iconic subscription, you have 12 months and 24 months. Get enrolled to 24 months, use my code to get the discount on this price. Now, let me tell you about Evolve for GATE 2022 and Ascend for GATE 2023. There are batches that have already started, and there are batches that yet to be started in this month. So get subscription to that, and let's see about the combat.
It's time to experience something glorious. Unacademy Combat. Compete, crack, conquer.
A challenging GATE contest engineered to give you an experience like none other, where you put your knowledge to test
and battle it out with a test
to bring out the best in you. Unacademy Combat is the most competitive, gamified contest for GATE till date, with the best of the questions by best educators,
with detailed video solutions from top educators right after each contest.
Combat live with peers to get real-time rankings and win big.
Participate in every contest to improve your rating.
Challenging contests every fortnight or alternate Sunday. Live ranking after every question. Big rewards for top rankers. Your passion to crack GATE.
Good evening, Raju.
Your
Welcome to
Unacademy.
Unacademy.
Your dream deserves this. Fuel your inner fire for the ultimate GATE challenge. Unacademy Combat. Register now.
We also have Iconic subscription. That was about the iconic subscription and combat and evolve and ascend also. We have work for GATE 2023 for electrical students, early start extra edge batch also for 2023 ECE, work for GATE 2023, and we also have Spark batch for 2022 ECE. The batch has already started and there are other batches that are upcoming. There is another Spark for GATE 2022 for electrical students as well. So the topic for today is we are just trying to revise the network analysis course. So let's try to do that. I would just give you a glimpse of what we have done in the previous session. Revision 1 we have done, complete chapter 1, or you call it as unit 1 revision, which was something like this. We have done what was topology and revised the basic concepts, also incidence matrix, tie set matrix and cut set matrix as well. Then we discussed magnetic circuits. We discussed the self-inductance, mutual inductance, coefficient of coupling, dot rule and ideal transformer also. Now coming to the second chapter, let's see the second unit or the second chapter. What is the second chapter is? It is actually time response, or you may also name it as transient and steady state response analysis. This is one part and the other part is resonance. So today we'll start up with resonance first, then we'll move on to the transients and steady state analysis. So let us look at what is resonance first. Resonance is, Shivakumar, good evening. Any circuit is said to be under resonance. First one, if the power factor of, if the power factor is unity, the power factor of the circuit is unity, or you can also say voltage and current are in resultant, applied voltage and resultant current are in phase, or nothing but the same thing, phase angle between V and I is 0 degrees. Right, so this is nothing but a circuit is said to be under resonance. So let's say you have a circuit this way, which is connected to some load which is excited with some AC excitation. This is a circuit or a network. This is I, this is V. If V and I both are in phase, that is cos phi is equal to 0 degrees, cos 0, then you can say that the circuit is under resonance. So we have two types of resonance circuits. One is series resonance and the other one is parallel resonance. Now let's look at series resonance. So in a series resonance circuit, what do we have is, we will consider a series RLC circuit. We will consider series RLC circuit. Let's consider that resistor, inductor and a capacitor excited by some source. So this is V R JXL minus JXC. This is I. Now let us first write What is the impedance of this circuit? Impedance is Z is equal to R plus JXL minus JXC. This is L, because resistor, inductor and capacitor all are in series, and this is R plus JXL minus JXC. Now let's write what is the current. I is equal to V by Z. Let's say this is Vs. So Vs by Z is R plus J XL minus XC. You can also write this as R plus J into XL minus XC. Now coming to the third one, under resonance. When does a series circuit is said to be under resonance is, let us say you have Z is equal to R plus J into XL minus XC, and V by I is equal to R plus J into XL minus XC or Z. V and I are to be in phase. Implies, what does that imply? What does that imply when V and I are in to be phase? Z must be real. For the Z to be real, that means Z is equal to R. So therefore, you can say under resonance, imaginary part of Z is equal to 0 or XL minus XC is equal to 0. That is XL minus XC is equal to 0, but XL is equal to XC. Therefore, for a series resonance circuit, XL is equal to XC. That is inductive reactance is equal to inductive reactance is equal to capacitive reactance. Now we can find at what frequency does this happen, because we know XL is equal to omega L and XC is equal to 1 by omega C. Now if you just try to plot this, what will happen? Before that, let's find at what frequency does this happen. So what are we going to find now? We are going to find the fourth one, resonant frequency. The frequency at which, what is this resonant frequency? Frequency at which V and I are in phase, or XL is equal to XC. So that is XL is equal to XC, omega L is equal to 1 by omega C. Can I write omega square is equal to 1 by LC? Yes. What is omega? 2 pi f naught. Let's call it as f naught under resonant, right? So omega naught is equal to 1 by LC. So can I write it as 4 pi square f naught square is equal to 1 by LC. So f naught is equal to, f naught square is equal to 1 by 4 pi square LC. F naught is equal to 1 by under root of 4 pi square LC. So finally you can write it as f naught is equal to 1 by, you can take 4 common and pi also common. So this is the resonant frequency in hertz. So the resonant frequency is f naught is equal to 1 by 2 pi root LC hertz. As we know, we'll try to do one more thing. Fifth one, impedance curve. We'll try to plot this. Impedance or reactance curve. You can also draw reactance curves. Now what is that? Let's see. First we'll plot reactance curve, then we'll plot impedance. XL is equal to omega L, XC is equal to 1 by omega C, XL is equal to 2 pi FL, XC is equal to 1 by 2 pi FC. Can I say XL is proportional to frequency and XC is inversely proportional to frequency? So what can you draw then? So if this is JXL or this is JX, yeah, this is JX, this is also JX, this is minus JXC plus JXL. Let's call this way, and this is omega. Now we know XL is proportional to F or XL is proportional to omega, and XC is proportional to 1 by F or XC is proportional to 1 by omega. So can I take this way? This is XL, and can I draw this way? Yes. So this is XL and this is XC, and there is another line here which you can draw here in between, and this frequency is omega naught or F naught. So these are reactance curves or XL and XC versus frequency. Now let's do the next one, sixth one. Instead, I'll just only take reactance curves here as the fifth one, and let us see sixth one as impedance. Impedance versus frequency. So what is impedance versus frequency? Impedance is Z is equal to R plus JXL minus XC. Now let us say at omega is equal to 0. Can I write it as R plus J into omega L minus 1 by omega C? Yes. Next, at omega is equal to omega naught and at omega is equal to infinity. What can you write the value of mod Z? This can be infinity. Mod Z, it is R, and mod Z again infinity. So I'll try to plot this with respect to omega. This is mod Z with respect to omega. So you have at 0 frequency, you have some infinity value, and this is some value of R, this is some minimum value. So Z is minimum. What is that value of R? And it is again, so you can draw a curve like this, and then again it is increasing to infinity. Yes, this is impedance curve or impedance versus frequency. Impedance versus frequency. Now let's try to take the seventh one, current versus frequency. Current versus frequency. Now as we have seen, as we know, I is equal to V by Z is equal to V by R plus J into XL minus XC, or V by R plus J into omega L minus 1 by omega C. And we have seen at omega is equal to 0, at omega is equal to omega naught, and at omega is equal to infinity. What was the value of mod Z? Is infinite, and here mod Z is R, here mod Z is infinite, which will imply, what does this imply? If these are the values of mod Z, what is the value of I? I is equal to 0 amps, I is equal to V by R amps, and I is equal to 0 amps. If you try to plot this current versus frequency curve, if you try to plot this current versus frequency curve, I versus frequency, it is 0 at this point approximately, and it is maximum at resonant frequency, then it is again decreasing. So this value is omega, sorry, at omega naught. What is the value of I? Is V by R, this value, maximum value. So I maximum is equal to V by R. Here Z minimum is equal to R. Alright. So these are the current and impedance curve. Or this graph is current versus frequency curve, and this is impedance versus frequency. So from these two, what can you conclude? At resonance in series circuit, you can say that at resonance in series circuit, impedance is minimum and current is maximum. Current is maximum. Now let's try to look at the bandwidth. What is bandwidth? It is the range of frequencies. It is the range of frequencies over which the power is half of its maximum value, or current is 1 by root 2 times its maximum value. That is, you can write, just draw this diagram. At this point, or even you can just take this term like this, at these values 1 by root 2 times, this is 1 by root 2 times. At this point, if you just take current versus frequency or power versus frequency, I here is I by root 2 or power is P by 2. Here P is P max, I is I max. What is I? V by R. So you can write I is equal to V by Z. So what is Z? Mod Z is equal to root over R square plus XL minus XC whole square, since Z is equal to R plus J into XL minus XC. Therefore, you can write this is this range of frequency. This range of frequency. This is lower cutoff frequency. This is higher cutoff frequencies. This range is called as bandwidth. So you can write I is equal to V by mod Z is equal to V by under root of R square plus XL minus XC whole square. So at half power frequencies, that means omega L and omega Z, what is I is equal to I naught by root 2. So substitute that I naught by root 2 in this place, substitute this is equal to V by root over R square plus XL minus XC whole square. But you know I naught is equal to V by R, that is current at resonance. So I naught by root 2 is equal to V by under root of R square plus XL minus XC whole square. Now you can write this as V by root 2 into I naught is V by R, I'll write it as 1 by R is equal to V by under root of R square plus XL minus XC whole square. You can cancel these terms and write R square plus XL minus XC whole square root over is equal to root 2 into r. So squaring on both sides, just squaring on both sides, what do you get? R square plus xl minus xc whole square is equal to 2r square. So take this r square to the other side. So you can write r square is equal to xl minus xc whole square, or xl minus xc is equal to plus or minus r. So you can write, what is xl minus xc? Omega l minus 1 by omega c is equal to plus r. Omega l minus 1 by omega c is equal to minus r. So we need to write the frequencies. So we'll take omega l, because these are the values at two different frequencies. Ramchandra Kumar, good evening, welcome to Unacademy. So omega 2l minus 1 by omega 2c is equal to r. Omega 1l minus 1 by omega 1c is equal to minus r. What you'll do is you just need to add these two. Add 1 and 2. Let's call this as 1 and 2. So you can write omega 2l minus 1 by omega 2c plus omega 1l minus 1 by omega 1c is equal to 0. So you can write, take common l. L if you take common, omega 2 plus omega l minus 1 by c if you take common, 1 by omega 1 plus 1 by omega 2. Can I write it as L omega 2 plus omega 1? Write this as L into omega 1 plus omega 2 is equal to 1 by c into omega 2 plus omega 1 by omega 1 omega 2. Can I cancel these two? Yes. What do you get then? You get omega 1 omega 2 is equal to 1 by LC. You can write 2 pi f1 into 2 pi f2 is equal to 1 by LC. So f1 f2 is equal to 1 by 4 pi square LC. Now you know that 4 pi square LC is actually what? So you write f1 f2 is equal to 1 by 4 pi square LC, but 4 f naught is equal to 1 by f naught square is equal to 4 pi square LC. So then you can write f1 into f2 is equal to f naught square. This is very important derivation. So f naught square is equal to f1 into f2. Next, we already know this is the, so in order to derive this we have done this, actually bandwidth we need to know, so we did not yet do that. So let's try to find that. We know omega 2l minus 1 by omega 2c is equal to r, and omega 1l minus 1 by omega 1c is equal to minus r. Now subtract these two. Let's take this as 1 and this as 2. Let's take 1 minus 2. So omega 2l minus 1 by omega 2c minus omega 1l plus minus of minus 1 by omega 1c is equal to 2r, r minus of minus r. So you will get L if you take common, omega 2 minus omega 1 plus 1 by c if you take common, 1 by omega 1 minus 1 by omega 2 is equal to 2 into r. So you write omega 2 minus omega 1 plus, you can write 1 by LC into omega 2 minus omega a1 by omega 1 omega 2 is equal to 2r by L. You can write this as omega 2 minus omega 1 plus 1 by LC omega 2 minus omega 1 by omega 1 omega 2 is equal to 2r by L. But you know omega 1 into omega 2 is equal to, you can just see here, 1 by LC. So you can replace this by 1 by LC and you can cancel these two. Therefore omega 2 minus omega 1 plus omega 2 minus omega 1 is equal to 2r by L. So 2 into omega 2 minus omega 1 is equal to 2r by L. You can cancel this. Omega 2 minus omega 1 is equal to r by L. So omega 2 minus omega 1 is equal to r by L. 2 pi f2 minus 2 pi f1 is equal to r by L, or you can write f2 minus f1 is equal to r by 2 pi L, r by 2 pi L. This is the bandwidth in hertz. Therefore bandwidth f2 minus f1 is equal to r by 2 pi L hertz. This is the final bandwidth expression. Right, so we have seen this. Let's go back and see what we have done till now. We have seen what is a resonant circuit. Any circuit which has power factor 1 or whose V and I are in phase and phase angle between them is 0, that is said to be a resonant circuit. Then types of resonant circuit, we have seen series resonant circuit and parallel resonant circuit. Then yeah, then we have seen series resonance. We have considered an RLC series circuit and written its impedance and current. And under resonance, V and I must be in phase, right? Or it must be unity power factor, so Z must be real. Imaginary part must be 0. So under resonant, XL minus XC is 0. So for a series resonant circuit to be under resonant, XL must be equal to XC. Inductive reactance is equal to capacitive reactance. So resonant frequency is the frequency at which this V and I will be in phase, or XL is equal to XC. From that you will get F naught is equal to 1 by 2 pi root LC, and you want to draw the reactance curve. So we know XL is directly proportional to F and XC is inversely proportional to F. From XL equal to omega L and XC is equal to 1 by omega C. Then we have drawn that reactance curves. XL is a linear graph, XC is an inverse graph. And impedance versus frequency, we have written the impedance Z is equal to R plus J into XL minus XC, that is at omega 0, Z is infinity, and at omega is equal to omega naught, Z is R, and at omega is equal to infinity, Z is infinity again. So that's how we draw impedance curve. Then we draw the current versus frequency. So at omega is equal to 0, as impedance is infinity, current was 0, and similarly at omega is equal to omega naught, impedance was R, therefore I is V by R, or Vs by R. And at omega is equal to infinity, you can say Z is infinity and I is 0. So this is impedance versus current versus frequency. Current is maximum, the value is V by R. Now at resonance in series circuit, impedance is minimum and current is maximum, and we try to find the bandwidth. It is a range of frequencies over which the power is half, or at half power frequencies the current is 1 by root 2. Using that we try to determine the value of, first we try to determine the relation between f0, f1, f2, which is f0 square is equal to f1, f2, or you can also write this as f0 is equal to root f1, f2. Sometimes you'll be asked to derive this. Derive f0 is equal to root f1, f2. And then you can also check this, subtract these two and find the bandwidth. This can also be the expression of bandwidth, or this is the expression of bandwidth. Now let us take voltage across inductor. This the same point we have to try. Yeah, 7th, 6th, 7th, 8th was bandwidth. 9th voltage across inductor. What is voltage across inductor expression? You know, you have a resistor, inductor and a capacitor. So voltage across resistor is VR, voltage across inductor is VL, voltage across capacitor is VC. So VL is equal to I into JXL. This is I is at I naught. So VL is equal to V by R into JXL. You can also write V by R into J into XL is omega L. So VL is equal to V into J into omega L by R. So VL is equal to J into V into, you can write this as Q naught, where Q naught is the quality factor. Q naught is quality factor. Or you can also write it as VL is equal to VQ at an angle plus 90 degrees. VQ at an angle plus 90 degrees. So that's how we call this that is quality factor is equal to VL by V. So we call this as voltage magnification circuit, and you can also find the Q naught is omega naught L by R, and you can also write voltage across resistor or voltage across capacitor. Let's write it down first. Voltage across capacitor. So VC is equal to minus JXC into I naught. VC is equal to minus XC is 1 by omega naught C into V naught V by R. So VC is equal to minus JV into Q naught. Here Q naught is equal to 1 by omega naught RC. So you can write quality factor Q naught is equal to omega naught L by R, or Q naught is equal to 1 by omega naught CR. Or you can also write this VC as V Q naught into minus 90 degrees. Now let's write the relation between Q naught and bandwidth. Let's write the relation between Q naught and bandwidth. So what is Q naught is equal to, or bandwidth is omega 2 minus omega 1 is equal to R by L, and Q naught is equal to omega naught L by R, or you can write R by L is equal to omega naught by Q naught. So write this down here. So omega 2 minus omega 1 is equal to omega naught by Q naught. So Q naught is equal to omega naught by omega 2 minus omega 1, or you can also write it as 2 pi f naught by 2 pi f2 minus 2 pi f1, that is f naught by f2 minus f1. So Q naught is equal to f naught by bandwidth. So this is the relation between Q naught and bandwidth. Now let's write a question problem based on this. A series RLC circuit has R is equal to 0.2 ohms, L is equal to 10 Henry, C is equal to 5 nanofarad. Determine resonant frequency, quality factor and bandwidth. So let's try to write the question. So given R is equal to 0.2 ohms, L is equal to 10 Henry, C is equal to 5 into 10 power 9 farad. So how do you do this? You know, f naught is equal to 1 by 2 pi root LC 1 by 2 pi root 10 into pi into 10 power minus 9. You get 712 hertz approximately. Then let's try to do what is quality factor. Q naught is equal to omega naught L by R, that is 2 pi f naught L by R. So 2 pi into f naught is 712 into L is 10 by R is 0.2 will give you 223,605.68. And finally you need to find bandwidth is equal to R by 2 pi L, that is 0.2 by 2 pi into 10 will give you 3.18 into 10 power 3 hertz. So this is how you will determine the values of f naught, q naught and bandwidth. So this is the first question. Now let's take the other question. Second question. Question says a series RLC circuit resonates at, although we have done the same problems, once again I am trying to give it the same information in this revision session. Given that R is equal to 10 ohms, L is equal to 0.2 millihenry, determine the value of C. So let's write what is given to us first. Given R is equal to 10 ohms, L is equal to 0.2 into 10 power minus 3 Henry, and F naught is given as 600 Hertz. So can we write F naught is equal to 1 by 2 pi root LC, implies you can write F naught square is equal to 1 by 4 pi square LC, or you can write C is equal to from that as C is equal to 1 by 4 pi square F naught square L, 1 by 4 pi square F naught 600 square into L 0.2 into 10 power minus 3. This will give you C is equal to 3.52 into 10 power minus 4 farad. This is how you can determine the value of C for the given question. So this was all about the resonance. Let's once try to see what we have done. We have done in resonance, series resonance actually. So let's try to complete the parallel resonance, then we'll take up what we have done. So let us consider parallel resonance. There are so many circuits of which we are considering only one circuit here. Let us consider a coil with some internal resistance is connected in parallel with a capacitor, and this value is R, this is JXL minus JXC, and combinedly we'll call this R plus JXL as Z1 and this capacitor as Z2. For ease of calculations, this as Vs and this as IAR, anti-resonant current. Now let us write what is Z1 is equal to R plus JXL and Z2 is equal to minus JXC. So what do you get from this Z1? Y1 is equal to 1 by R plus JXL, Y2 is equal to 1 by minus JXC. So can I write Y1 is equal to R minus JXL by R plus JXL into R minus JXL in order to separate real and imaginary parts. So Y1 is equal to R minus JXL by A plus B into A minus B, A square minus, so that will become R square plus XL square. And similarly Y2 is already, you can write J in the numerator, J by XC. This is Y1, this is Y2. So what is total Y? You can simply write Y1 plus Y2. You can it is easy to write in terms of admittances than in writing in terms of impedance. So the total admittance is y is equal to y1 plus y2. Therefore y is equal to, what is y1? R minus jxl by r square plus xl square plus j by xc. Can I separate real and imaginary parts? Real and imaginary separation. So what can I write that? Y is equal to r by r square plus xl square minus jxl by r square plus xl square plus j by xc. So what can you write from this? You can write y is equal to r by r square plus xl square plus j into 1 by xc minus xl by r square plus xl square. And if you observe this, for the circuit to be under resonance, for circuit to be under anti-resonance or under resonance, you can say imaginary of y must be equal to 0. What is the imaginary of y that you see here? 1 by xc minus xl by r square plus xl square must be equal to 0. So what is xc? 1 by omega c. So can I write omega rc by 1 minus omega arl by r square plus omega ar square l square is equal to 0. Now you can write this as omega ar is anti-resonance is equal to omega arl by r square plus omega ar square l square. Can I cancel these two? So what do you write? C is equal to L by r square plus omega ar square l square, or you can write in other words r square plus omega ar square l square is equal to L by C. Omega ar square l square is equal to L by C minus r square, or omega ar square is equal to L by C minus r square by L square. That is L by C into 1 by L square minus r square by L square. You can cancel this two. So omega ar square is equal to 1 by LC minus r square by L square. So you know omega ar is equal to 1 by LC minus r by L whole square, or the square. Omega ar is equal to root over 1 by LC minus r by L whole square. So this is anti-resonant frequency of the given parallel circuit, or we can also write it as 2 pi far is equal to root over 1 by LC minus r by L whole square, or far is equal to 1 by 2 pi under root of 1 by LC minus r by L whole square. So this is also the anti-resonant frequency. This is also the anti-resonant frequency FAR, 1 by 2 pi under root of 1 by LC minus R by L whole square. So this is how you will determine the anti-resonant frequency of a parallel resonant circuit. Now you will consider susceptance curve. Let us consider susceptance curves. So we know Z is equal to R plus Jx. So Y is equal to G plus JB. What is G is equal to 1 by R. X is equal to 1 by B. Or you can write B is equal to the other way. So So what is BL is equal to 1 by XL. BC is equal to 1 by XC. So BL is equal to 1 by omega L. BC is equal to omega C. So from this we can say that BL is proportional to omega, BC is inversely proportional to the other way around. BL is inversely proportional to omega, BC is proportional to omega. Or BL is proportional to 1 by frequency or inversely proportional to frequency, and BC is proportional to frequency. So you can draw resonant curve or susceptance curve as, so this is BC, yeah, this is BC, BC, this is minus JBL, and you can draw this as, this is BL, and the line between these two where there is a resonant frequency, this is anti-resonant frequency FAR. Or we can also represent this as this way. Just take down BL. If we take BL in the top, this is this is JBL and minus JBC. So this is minus BC, and this line is BC, and the other one is BL. This is BL. Yeah, this is BL, this is BC, linearly with respect to omega. And this is the region where you get FAR, anti-resonant frequency. This frequency, where you get it exactly. Yeah, this frequency, where you have BL minus BC or BC minus BL. Imaginary part of admittance is equal to 0. Similarly, if you try to plot impedance and current versus frequency or admittance, also you can just take impedance, admittance, and current versus frequency. If you just take this down, you can just simply mark this like this. So this is impedance versus frequency, admittance versus frequency, and current versus frequency. So impedance is this part, which is maximum at anti-resonance FAR, and so admittance will be reciprocal of impedance, which is minimum. So this is at anti-resonance. So because this is impedance is maximum at resonance, current will be minimum at resonance. So this part is FAR. So we can write this as, this is Z max, this is Y minimum, and I minimum. So these are the values of impedance. Srinivas, good evening. Soumya, good evening. Welcome to Unacademy. So if you look at what is the quality factor, you can just write it down. Quality factor Q is equal to omega naught L by R, or 1 by omega naught CR. So R square plus omega AR square L square is equal to L by C. So You can write r square common and write 1 plus omega square L square by r square is equal to L by C, or r square into 1 plus QAR square is equal to 1 L by C. So just write it down as 1 plus QAR square is equal to L by C into 1 by R square. So QAR square is equal to L by R square C minus 1. This is one expression for QAR, or you can write 1 plus QAR square is equal to L by R square C, or L by RC into 1 by R. So what is this? 1 plus QAR square is equal to L by RC is ZAR into 1 by R, impedance at resonance. So you can write ZAR is equal to R into 1 plus QAR square. So Z anti-resonance is equal to impedance at anti-resonance is equal to R into, so you can write Z anti-resonance is equal to R into 1 plus QAR square, or you can also write QAR square as QAR square is equal to L by R square C minus 1. Right, so this is how you will determine now let's take one question and try to solve it. For parallel resonant circuit, determine the value of C, determine the value of C such that the given circuit is under resonance. The given circuit is under resonance, and the circuit is given like this. You have a resistance, an inductance, a capacitor, and which is excited by some source of 100 volts. These values are given as 5 ohms minus plus J 10 ohms, and this is C is variable. So what can you write? R is equal to 5 ohms, L is equal to, or XL, JXL is equal to J 10 ohms, implies XL is equal to 10 ohms, V is equal to 100 volts. So what is Z1? You can write 5 plus J 10 ohms, and what is Z2? Z2 is minus JXC. So we can write Y1 is equal to 1 by 5 plus J10, and Y2 is equal to minus 1 by JXC. So you can write Y1 is equal to, by using component dividend, to 5 minus J10 by 125, 5 square plus 10 square, 10 square 100, 5 square 25, and Y2 is equal to J by XC. So total admittance, you can write total admittance Y is equal to Y1 plus Y2. So Y is equal to, what is Y1? 5 minus J10 by 125 plus J by XC. We know that under resonance, imaginary part of Y is equal to 0. So separate that imaginary part. So you write 5 by 125 plus J by XC minus J10 by 125 by 10, or 12.5, will give you C is equal to 5 by 125 omega. So this is the required value. Likewise, you can solve many problems. This is about the resonance completely. So we have done resonance. In resonance, we have done what is series resonance and parallel resonance. In series resonance, we found F naught, bandwidth, Z versus frequency, I versus frequency, as well as F naught is equal to root F1, F2, and yeah, these are some of the things. In parallel resonance, we found what is FAR and what is ZAR also. And we try to solve some problems based on them. Now let's try to see transient and steady state analysis. I'll just give you an introduction and we'll revise the same in the next session. So whenever any system or a subject is, the circuit is subjected to some disturbance, or if its state has been changed, then the circuit will be circuit will undergo transients. Circuit will undergo transients if there is any disturbance, or if there is any change of state from on state to off state, off state to on state, or sudden so it takes, after this transients, it takes some time to reach steady state. So that time is called as, the time it takes to reach steady state is called as transient time, and the response in that period is called as transient response. And after this, in transients, that is, once these transients die out, the response that you get is a steady state response. So we'll know more about this transients and steady state response, and we'll try to analyze the rest part of this transients and steady state response in the next session, next revision session, and we'll try to complete that in the next class. As well as what we shall do is we'll also take up revision classes for the third chapter, two ports, as well as for the transient transmission lines 1 and 2. So once again, as I always tell you, we have #1 study channels on Unacademy, and like this video, share this video, and you can use my code to get the maximum discount on your Unacademy subscription. Hit on this bell icon to get notification of my classes. You can also join us on Telegram, and do subscribe. Don't forget to subscribe to Unacademy Let's Crack GATE and ESE, and you can also like and share this video. Once again, thank you all. Thank you for joining me today on this beautiful session on revision of resonance. Thank you.